It's recording now? Okay. All right. Okay, so new little concept we're going to talk about. Not anything too fancy. If I have let's say a tire, for example, and we heat the tire up, what's going to happen to the pressure inside that tire? It's going to go up. The pressure is going to go up. So I'm going to erase this. So when the temperature outside the tire, outside of anything, if the temperature starts to go up, what's going to happen to my pressure? Good, the pressure will also go up. So when temperature goes up, what else goes up? Pressure. That's exactly right. Now, let's think about what happens to a mixture of temperature and pressure, right? Let's say of water and water vapor, and I increase the pressure on that. What happens to the saturation temperature? Let me rephrase that. If I have water with liquid and vapor, and I raise the pressure on water, what happens to the boiling point? It goes up. Okay, so let's rephrase it again. If I have water with water and water vapor, and I raise the pressure on that, what happens to that water's saturation temperature? It's going to go up. Say I change the word for saturation and boiling. They're interchangeable.
Oh, yeah.
So, yes, right on. Love it. So, when my temperature goes up, the pressure is going to go up. But also, if I have liquid and vapor at the same time, and my pressure goes up, what else is going to go up? Now we got it. So if my temperature goes up, my pressure goes up, and if my pressure goes up, my saturation. That's right. And if my temperature goes down, what happens to my pressure? What happens to saturation? That's exactly right. Exactly right. So here, no. There's vapor here, and there's also liquid here as well. My hand has heat, right? Body temperature, we're creating heat. I'm actually burning calories, using energy from one source to another. So if I put my hand around the bottom of this glass ball, is heat going to go into this? Yes, because it's at room temperature 72 degrees. My hand is warmer than that, I will have heat transfer. So I'm going to put my hand around it, and it's going to raise the pressure inside, right? Yes. By raising the pressure, it has raised and pushed that fluid up to the top. Right? If I look now, there's no liquid, hardly any liquid left at the bottom. But if I put more heat at the top, the pressure also increases, and it pushes it back down. It's also pushing the gas down, and you see it bubbling. Okay? So that's just a connection between temperature and pressure. Yesterday we had the balloon, put the balloon in the freezer, and as the temperature dropped in the balloon, the pressure in the balloon dropped, so the balloon contracted, right? Yes. We heated it up and it expanded. This morning we tried that, but I got the balloon a little bit too hot. The pressure went up past its maximum, and it popped. There's still little pieces of the balloon. It was definitely a cooked problem. So, but this is just an example of temperature and pressure. But we also have a correlation with temperature and pressure and also saturation. On this unit, even if this unit was off, and I put heat against this coil, I'm applying heat on this coil, what's going to happen to the pressure inside? It's going to go up. That's exactly right. Now, as that pressure goes up, is it going to also affect my saturation point, my condensing point? Yes. Yes, it will. And if I put ice all around this, what happened to my pressure inside? It's going to go down. What happened to my saturation temperature? It's going to go down. All right, so is it true that the outside temperature will affect the pressure inside this coil? Yes. Now, if it's running, I'm creating high pressure, but the outside pressure will still affect the pressure inside the coil. It's still going to have an effect on it. That's what's cool about it. So let's think about this. The heat during the day goes up. The compressor's running. Everything's running. the temperature of the air goes up. So there's more heat touching this coil. That means there's more heat touching it. It's not cooling the refrigerant off as fast, right? So if there's more heat applied to this coil, what's going to happen to the pressure inside this coil? So more heat means more temperature. So the temperature outside goes up. What's going to happen to the pressure of the refrigerant inside? It's going to go up. Now if my pressure goes up, what's going to happen to my saturation temperature? It's going to also go up. So when the temperature outside goes up, the pressure outside is going to go up, and my saturation, change of state from liquid to vapor, rejecting heat, latent heat, all that is going to go up to a higher point. As the temperature outside drops, there's less heat acting against it. There's better heat transfer. So as the temperature outside drops, that means there's less temperature affecting this coil. What's going to happen to the pressure on it? It's going to drop. Now, as my pressure drops, what happens to my saturation temperature? It also drops. You see how it's an automatic connection? I don't have to speed the motor up or anything. This compressor runs at one speed. No matter what, it runs at one speed. The speed doesn't change. The actual natural science behind temperature and pressure is what changes that automatically. If I have enough refrigerant there, it will automatically change and be good.
That's cool.
It is cool. It's science. It's awesome.
Because you would think the compressor would work harder.
And as it gets hotter, that's a good point. As it gets hotter, the pressure goes up even more, and it affects the compression ratio. The pressure ends up having more work going on. There is more back pressure pushing against the motor, but it still turns at the same speed. It just is going to use more electricity. The compression ratio is going to change. A lot of stuff's going to change, but the motor can't speed up. It can't go faster. These, what we use for what we're talking about, they don't change. They're the same speed all the time. Okay? Interesting? All right, so now let's think about if I put plastic right here. What am I blocking if I put plastic right here? I'm blocking airflow. I'm making the heat leave the refrigerant, and the heat's trying to go to the air, right? So the air is also cooling off the refrigerant. So if I put plastic right here, I'm blocking airflow. So if I put plastic in front of the radiator of your car and had the engine run, what's going to happen to the temperature of the car? It's going to go up because I'm moving less air across it, right? So if I put plastic across this and I'm blocking air to it, this is still giving off heat. So what's happening to the temperature around this coil? It's getting hotter. So now the temperature is going up in this area. As the temperature goes up, what's happening to the pressure inside those pipes? They're going up. Now, as my pressure goes up, what else is going up? Your saturation temperature. So yesterday, when we blocked that with plastic, it was causing less air transfer. It was changing the heat transfer. The heat staying here instead of being pushed away by the fan. The heat staying here. Now we have more temperature right here, which means more pressure inside. More pressure inside means the pressure goes up. And the pressure goes up, the saturation temperature also goes up. Does that make sense? Yes. That's what's happening. That's what was happening yesterday when we were changing that and adjusting that. And if you guys see, the pressures are changing all the time. The temperatures lines are changing all the time. We're looking for something more stable, such as superheat and subcooling. It's going to be much more stable. We've got several things to go before we get there. Now here's the catch, is the inside pressure has a few variables going on. As my outdoor temperature goes up, what's happening to my outdoor pressure? It's going up. Now there's pressure pushing against that liquid, right? Now if there's more pressure pushing against the liquid, and this is just a fixed hole, and there's more pressure pushing that liquid harder, what's going to happen with the refrigerant coming to the hole?
More liquid.
More liquid will be pushed through the hole. If I have a sprayer on a water hose, and I have a fixed size hole on it, and I open the water up more, there was more push of water against it, will more water come out of the hole?
No.
Yes. Yes, it will. Try it. If you have a water hose, try it. Have a fixed hole, just turn one of the knobs to one setting, and then as you open, even a loose water hose, open the faucet all the way up, and you'll see that more water is pushing out. More volume, even on the sink. You can do it in the sink. Open the sink a little bit. That's a fixed hole where the water's coming out. The size of that hole doesn't change, does it? Well, if you open the faucet more and you have more pressure pushing against it, more water comes out, right? So as the outdoor temperature goes up, what happens to the pressure right here? Goes up. Now I have more pressure pushing more liquid refrigerant. So what's going to be happening on the other side of this hole here?
Pressure's going up.
more liquid's going to be coming in this way, which means I have more pressure on this side. So the outdoor temperature will affect the outdoor pressure, which will have an effect on my indoor pressure. Now, as my outdoor temperature starts to drop, like at night, the outdoor temperature starts to drop, what's happening to the pressure here? It's dropping. Now I have less push through this hole. Does that have an effect on this side? Yes, I'll have less pressure on this side as well. Less refrigerant coming through. We're going to be revisiting this thought process later. So the outdoor temperature affects the outdoor pressure, which affects how much refrigerant is coming through this meter device, which will have an effect on the indoor pressure. Kind of cool, huh? Now let's think of it this way. What's the opposite of the condensing coil?
Evaporation.
What's the opposite of the high side?
Low side.
What's the opposite of changing from a vapor to a liquid?
Liquid to a vapor.
Okay, so this thing's like the opposite of it in every way, pretty much, right? So here, if I'm trying to cool this room and I want to take the heat out of this room, I'm going to first take the heat out of the what?
Air.
Out of the air. Good, because it's air conditioning, right? It doesn't have relatives it's giving money to. It's not that kind of air. It's air conditioning, right? So we're going to have to move the air across the evaporator coil because the heat is in the air. Yes, the heat's in the air. So I'm going to move the heat or the air across this evaporator coil inside. The heat from the air is going to leave and go to the refrigerant, right? We get that concept down?
Yeah.
Good. So as the temperature of the air starts to drop, what is happening to the pressure of this evaporator coil? It will also drop. What will happen to my saturation temperature? It will also drop. Right? So the temperature of the air inside the house will have an effect on the suction pressure, and so will the outdoor temperature. Now, as the temperature in the house starts to go up, there's more heat in the air, and the more heat's reacting against this, what's going to happen to my suction pressure? It's going to go up. And what's going to happen to my suction saturated? It's going to go up, right? Automatically adjust. Now, what happens if I have, say, a dirty filter and I'm blocking airflow? I have less airflow going across this evaporator. If I have less air, that means I have less what? Less surface area. I have less heat, right? So if there's less heat, less temperature reacting to this, that means my pressure is going to do what? The pressure will drop. And if my pressure drops, what's going to happen to my saturated temperature? It's going to drop. Once my saturated temperature, PSIG converted temperature, drops below 32 degrees, what's going to start happening to it? It's going to freeze. It's going to start creating ice. Ice is going to block airflow. If we block airflow, it's going to cause it to freeze faster, which is going to cause it to block more airflow, which is going to cause it to freeze faster. You see how it just continues on? Right? Pretty cool, huh? Right? Good. It is. It's interesting. It's amazing. This is just so much to this. I love this stuff. Never gets old. Always new stuff.
You send the ice up because they get airflow.
Yeah.
Because it's not enough heat. The heat's in the air. So if I either take the heat out of the air, lower the temperature in the house, that will affect it, cause it to freeze. Also, if I block the airflow, the heat's in the air, I have less air, aka less heat, that will cause it to drop. And also, there's several things, but I can also, what if I had less refrigerant? There's not enough volume here. If I have less volume of refrigerant, what would that do to the pressure out here? Less pressure. Now, I had less pressure here. What happened to the pressure here? It would drop. As my pressure dropped, what happens to my saturation temperature? It drops. So if I don't have enough refrigerant, my pressure will drop, my saturation temperature will drop. Once my saturation temperature drops below 32, what's going to happen? It's going to freeze up. What about if I had a clogged up metering device?
Freeze up.
I would have too much of a pressure drop, right? And if my pressure dropped, what else drops?
Saturation.
And if my saturated temperature drops below 32, the unit will freeze. What about if my filter dryer was clogged up and I had a pressure drop here, and then I went to my metering device and had another pressure drop? Pressure drops, and then once it drops below 32, it will freeze. I could have a kink in the line or a bad metering device, clogged line. I mean, any of those things can cause it. So the reason the unit will freeze is because the saturated temperature drops below 32 degrees Fahrenheit. The number one cause, we're going to visit this later, the number one cause is airflow. Dirty filter, bad fan, bad ductwork, block return, blah, 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 blah. The number 2 cause is low in refrigerant. What will cause it to be low in refrigerant? We'll come back to you. A leak. Find a leak. The number 3 cause is the temperature's too low. Either the temperature outside falls too low, and I don't have enough pressure pushing through, or the temperature inside drops too low. Some people like to have their temperature, the thermostat set at like 65, and that'll can cause it to freeze, along with the humidity in the air as well. You put a unit in Florida below 70, it's going to freeze quick. There's a lot of moisture in the air. And the last thing is a refrigerant restriction, something that's not getting through to here. And we're going to come back to this later, but at least gives you a starting point of why it freezes. Saturated temperature below 32. Done. That's the answer to the question. Now, things that cause that, the number 1 reason, airflow. Number 2 reason, low in refrigerant. Number 3 reason is temperature is too low, outside or inside. And the last reason is some kind of mechanical restriction. Now, we always come into this. I will get there, I promise. We always come into this. People always say, well, what if you overcharge it with refrigerant? So before we answer it, let's think about what an overcharge would be. Overcharge means I'm putting more molecules of refrigerant into this system, right? So if I add more molecules of air into your tire, what's your tire pressure going to do? Okay. So if I add more molecules of refrigerant into the system, what's the pressure on this side going to do? It's going to go up. So if I have higher pressure here, that means there's more pressure and more refrigerant, more molecules coming through this meter device. So what's going to happen to my pressure over here? It's going to go up. So will being overcharged cause the saturated temperature to be below 32? No. So being overcharged, will it cause it to freeze? No. But it is an issue because some people think only that it's low in refrigerant. So you may have a blocked airflow here. Blocked airflow. What's a blocked airflow going to cause? Temperature to drop, pressure to drop, saturated temperature to drop, right? So somebody comes through and says, well, it's freezing up, so I'm going to add refrigerant. So they're putting more molecules in over here. That pushes more over here, causes more refrigerant to go over here, which causes pressure to go up, and now it's not freezing. And they think, oh yeah, I solved the problem. But did they solve the problem? No. Here's what happens. Now that we're getting more liquid over here, I have more liquid. So the liquid overfills the evaporator coil. I have more liquid. I have too much liquid. I have more liquid that I can boil into a vapor. So what happens to my superheat? It starts to drop. Now that means I have less superheat. That means I have more and more liquid, right? Now I start getting liquid coming back to my compressor. And while I solve the problem today, I am killing that compressor. The compressor will die sooner or later. Well, eventually the compressor will get liquid and it will, you try to compress a liquid and it just snap and it will break. Something will break. Yep. And it happens a lot. So one of the big problems is most units in the U.S. are overcharged. They got too much refrigerant in them. Most of the units all across the U.S. are overcharged. People don't understand what refrigerant is one of the problems. They don't understand the refrigeration cycle. That's a big deal. A lot of people out there are like, oh, look, it's magical unicorn juice. And if magical unicorn juice makes cold, and this stuff is just magically cold, and if I put this into the system, although I don't know how it works, I know if I put this magical unicorn juice into the system, it will start blowing out cold air. And the more cold juice I put in, the more cold air I'm making. Is that anywhere possible? And I use the unicorn juice because we know that they're fictitious animals, right? Sorry to crush some of your feelings, but they are. And also, cold is also fictitious. We can't get there. And making cold is fictitious. We can't get there. So it all is fictitious. It's the fact of a substance changing state from a liquid to vapor, absorbing massive amounts of heat, absorbing heat because of a lower pressure, then raising the pressure to raise the boiling point, raise the condensing point, raise the saturation temperature to make it reject heat at a higher pressure and change state from a vapor back to a liquid so I have more liquid to boil again. That is refrigeration. That's what makes this work. There's tons of these refrigerants I can use. Different ratings on all of them, but tons of refrigerant I can use to make this happen. You, sir, had a question.
You put liquid into the evaporator, or you're worried that it can freeze. Isn't ice breathing or refrigerant breathing?
The ice on the outside. The refrigerant, it's boiling at this temperature, so it's going to be a long ways from freezing. But on the outside, what's in the air all the time, even on low humidity, what's in the air? Moisture. Yes, moisture is in the air. So if this temperature of the coil, the refrigerant's boiling at, say, 26, it's boiling at 26. But now on the other side of this, moisture from the air touches that. It takes the heat out of the moisture. The moisture turns from a vapor into a solid. It's called sublimation. And that solid starts to block airflow. Ice is actually a pretty good insulator. And then that causes more airflow to be blocked. And you end up with an ice maker. And if I want an ice maker, that's great. But if I have an air conditioner and trying to make an ice maker, it's not so good. Not so good at all.
I got a question you don't like.
Okay, what's up?
Is the dryer the can?
The can.
Yeah, you know they say change the can in AC. That's the dryer.
I don't think I've heard anybody say change the can in an AC.
Never heard that?
Is it on the liquid line? And is it small can-like, I guess? Then there you go.
I ain't heard that in years, but I just think about that.
Usually when people talk about a can, they're usually talking about that can of refrigerant or even a jug. A lot of times people call it a jug. Oh, go grab another jug of juice.
Yeah,
Go give me another jug of juice.
that's why I said it, 'cause
I'm like, no, we'll talk about one more thing too, but I want to talk about this first. Let's talk about refrigerant, baby. Let's talk about humidity.
Why are you reading this in
And this stuff? Love
Talk highly of
Oh, 410A? Oh, I'm not a fan of 410A. There's better. I'm a fan of propane as a refrigerant, which somebody forgot to remind me. Who is it? We're going to talk. Okay, we're going to come back to that. But before we get there, I think there's better refrigerants than this. But it's regardless. My opinion doesn't matter on that. This is what's being used most right now. It's great. I mean, I think R22 is a great refrigerant, but it's gone away, so it doesn't matter if you like it or not. This is what's in. We learned how to work on it. We'll get into some other ones later. But before there, I've opened this valve here, and I've hooked it up to this gauge right here. So I'm measuring what inside this tank? Pressure. I'm measuring pressure. Can you tell me what the pressure is there, sir?
Right around 200.
Okay. I'd concur with that. Just to make sure, let's have you double check his work. The red gauge.
Yes, 200.
200. There's 200 psi of pressure inside my tank. Right? So, do you know what else is inside this tank? Refrigerant. Now, if you wouldn't mind, you would pick this tank up for me, please. Okay? Want to concur with him? Maybe not over your tablet. Okay. So, you think there's any liquid in there?
Yeah.
Pretty good chance of that, right? Yeah. Try shaking it and see if you can feel anything sloshing around in there. You feel it sloshing around?
Yeah.
Yeah. So there's liquid in there. So there's liquid refrigerant. They just passed a new law recently that liquid is going to be heavier and it's going to go down, and vapor is going to be lighter and it's going to be at the top.
Wait, they passed that law?
Yeah, it finally passed. It's been hung up in for a while. It's finally gotten around to it. All right. So there is liquid and there is vapor at the same time, at the same place. What are we at?
Saturated.
Oh, bam, saturated. This is saturated. That means because it's saturated, I can take this PSIG and convert it to temperature. So, what refrigerant is this?
410.
The pressure was what? Oh, beautiful. And it's at what? Saturated. So that means you should be able to tell me a temperature, right?
76.
What'd you get? What's that?
70.
70 degrees. Let's go over and look at my thermostat. 72. So these aren't digital, so it's hard to see that number for exactly on there, but
Close.
pretty darn close. If I actually got a digital thermometer and put it on there and my digital set, I imagine it would be exactly on. It's at saturated, liquid and vapor together. I took my pressure and converted it to temperature. Does it not match? The temperature of the tank match the temperature-pressure chart, because it is, without a doubt, saturated. It's not changing state. It's not actively changing state, but there is liquid and vapor together, right? What happens if I drop the temperature of that tank?
It's gonna drop the pressure, it's gonna drop the saturation. And the saturation.
I'm gonna put this in the freezer. We'll revisit this a little bit. I forgot to take this out.
Put it in the microwave.
It's a plumber, the crack's showing. I have friends that are plumbers, I don't mean any disrespect, but. So if I put a fan across this, what would we have? Really? If we took the weight of this, could we find how much latent heat it would absorb?
Yeah.
If you grab a hold of this, how does that feel? How does that feel?
Feels cold.
No.
What?
Don't say it, I said don't say it.
You only got one.
Man,
Don't say it.
pass it to the next guy. You let me down. So how does how's your hand feel?
It feels
Less heated. The BTU, the heat from your hand, is leaving your hand and going into the cooler ice. There is heat transfer. Heat is leaving your hand and going to the cooler ice. Right? As we pass it around, everybody can see that. I just want you to be thinking about, because we talked about it,